Welcome to this explainer. Right, let's get straight into it. I want you to imagine the coastline, not just as some quiet beach where you'd go to eat an ice cream, but as a dramatic, ever-changing battleground straight out of an anime. I mean, we are talking about colossal clashes of natural forces, constantly shifting landscapes, and humans desperately trying to tame the completely untamable. For your A-level geography exams, making sense of this dynamic environment means we have to actually measure these epic battles. And the way we do that is by looking at something called a coastal sediment budget. To really wrap your head around this, just think of a dynamic beach like your own personal bank account. If you look at a standard financial budget, you've got your income, you've got your outgoings, and at the end of the month, you are either left with a surplus or a deficit. Well, a coastal system works exactly the same way. The inputs of sand and shingle, that's your income. The outputs, where sediment is literally washed away, those are your outgoings. A surplus means you have a growing beach, which we call accretion. But a deficit, that means your beach is in debt, and that leads to dangerous coastal erosion.
So, continuing with that financial metaphor, when you hit that income button way harder than the outgoings button, you get a positive sediment budget. In coastal terms, this net accretion builds up the beach, creating a massive protective buffer of sand and shingle against the waves. But if your outgoings outpace your inputs, you're looking at a negative sediment budget. And that leads to a really stark loss of sediment, basically stripping the beach bare and exposing the land right behind it to the full fury of the sea.
Okay, let's make sure we have the exact definition locked down for your exams. A sediment budget is defined as the balance of sediment volume entering, the inputs, and leaving, the outputs, a sediment cell, revealing the net balance. The absolutely crucial takeaway here is that net balance part. It's not just about listing what's randomly sitting on the beach. It's about calculating the final, bottom-line physical state of that entire coastal system. Section 1. The coastal system components. Let's look at how the coastal system boundary is actually laid out. The flows of energy and materials act as your inputs on the left. Now, once they're inside the system, these materials don't just magically vanish, right? They move through sediment flows and sit in sediment stores like beaches or sand dunes. Eventually, through various processes, some of this material exits as outputs on the right, and the environment itself is providing all the energy, the wind, the waves, the tides, that drives this entire machine. Zooming in on those specific inputs and outputs, we really need to categorize them into natural versus human factors. On the input side, nature is providing sediment through things like rivers, cliff erosion, and offshore transport. But humans, we also artificially pump up the budget through beach replenishment and land reclamation. Now, on the output side, nature removes sediment by washing it out into deep water or into estuaries. Meanwhile, humans are out there extracting sand and gravel through dredging. So it's this constant, relentless tug of war between natural forces and human activity. So, let's think about how this actually works in motion. Take longshore drift, the movement of material along the coast by the waves. If that is interrupted, would you consider that an input, an output, or a flow? Take a second to really think about it. Got your answer? It turns out it is a flow. It's not a standalone input, and it's not an output. It's the transfer mechanism. Think of it like a giant conveyor belt moving sediment along the coast from one store to another. Understanding this distinction is absolutely vital, because when humans mess with this flow, they disrupt the budget of the entire system.
Moving on to Section 2, Case Study, Shoreham Harbor.
We are traveling down to the south coast, about 7 kilometers west of Brighton, to Shoreham by sea to do a bit of data detective work. Let's establish the geography here. Shoreham by sea sits right on the coast, but there is this massive harbour smack in the middle, located right at the mouth of the River Adur. This harbour acts as a really strict artificial divider, effectively splitting the coastline into two totally distinct subcells, the West Beach subcell and the East Beach subcell. And here is the human intervention in all its glory. Two massive concrete breakwaters jutting straight out into the sea to protect that harbor entrance. Naturally, longshore drift flows from west to east here. But if sediment is allowed to just drift across the harbor mouth, it deposits right in the entrance, making the waterway way too shallow for boats to get in. So these strict artificial breakwaters were built specifically to block that flow. Okay, let's actually crunch the numbers for the West Beach subcell, which sits updrift of the breakwater. Just look at these inputs. We have 7,791 cubic meters coming in naturally from longshore drift. But wow, look at the human input. A massive 27,847 cubic meters of artificial beach replenishment. On the output side, humans are artificially extracting sediment for recycling, and get this, they're even loading 12,555 cubic meters into lorries to physically drive it past the breakwater, all while a little over 3,600 cubic meters is lost naturally to attrition. When you do the math, subtracting the total outputs from those total inputs, you get a net volume of positive 15,788 cubic meters. That is a massive surplus. So the West Beach has a highly positive sediment budget, which leads to wide, rapidly growing beaches that just accumulate vast amounts of material right up against that breakwater. But hold on, look at this stark contrast downdrift of the harbor at the East Beach. Check out that very first row under inputs. Longshore drift in, 0, none. That breakwater blockade is 100% effective. The only input this beach gets at all is the 13,245 cubic meters of artificial replenishment. Meanwhile, longshore drift just continues to pull sediment out and away to the east, alongside natural attrition, resulting in over 18,000 cubic meters of outputs. And here is the brutal result. Total inputs minus total outputs leaves the East Beach with negative 4,820 cubic meters annually, a severe, severe deficit. This coastal budget is heavily in the red, meaning the beach is literally being starved of sediment. So, let's synthesize the data with the physical reality for a second. If the breakwaters block the longshore drift, leaving a deficit of nearly 5,000 cubic meters a year, what actually happens to the physical environment of that East Beach? It erodes fast. It develops a severe sediment deficit. This right here is a classic example of coastal management trade-offs. The human intervention created an unintended consequence, protecting the harbor for navigation, which is great. But it also created a highly dangerous unintended consequence, the total starvation and rapid erosion of the East Beach. Section 3, Case Study, Hampton Pier. Tracing the timeline away from Sussex over to the North Kent coast is super fascinating. Back in the 1890s, Hampton Pier was constructed. Now, on this stretch of coast, the largest, most powerful waves arrive from the northeast, and they drive the longshore drift. The pier acted as a massive, rigid barrier to this energy. Fast forward to the 2020s, and you have severe landscape alteration. Just like we saw at Shoreham, interrupting that natural flow of sediment completely reshaped the entire coastal budget. It forced sediment to accumulate massively on one side, while completely starving the other side. Final section, number 4, human impacts and equilibrium. Zooming out to the big picture, the crucial point is understanding why any of these deficits actually matter in the real world. A negative sediment budget isn't just some math problem on a worksheet, it deeply impacts real stakeholders. For local residents, a shrinking beach removes their main buffer against storm waves, creating a massive flood hazard for their homes. For local businesses, no beach means fewer tourists, which deals a huge blow to the local economy. Harbor authorities end up facing skyrocketing management costs to artificially move all that sediment around, while local authorities are legally required to spend millions trying to mitigate these hazards. Which leaves us with this final, high-stakes balancing act. We know for a fact that human infrastructure breaks the natural sediment budget. But if removing a pier or breakwater is what's required to restore that natural equilibrium, who ultimately pays the price? Do we sacrifice the harbors and the coastal businesses to just let nature take its course? Or do we commit to spending millions, endlessly, artificially balancing the budget? It's a hugely complex geographical problem, and it's exactly the kind of critical thinking you need to bring to your A-level answers. Keep questioning the system, and thanks for exploring with us on this explainer.